everybody knows what a symplectic manifold is, but I don't know if it's a safe. Is it okay? Yes? Okay. So, so here's a symplectic manifold. I need to I'll need to recall I don't know if anybody can read my handwriting. Can you? The Poisson algebra structure on the smooth functions, and tell me to stop if this is boring. You've seen it before 16 times and things of that sort. So remember that we have the so-called Poisson bracket. It goes from C infinity of m cross C infinity of m to C infinity of m. And it has with two properties. One is that this bracket makes C infinity of m into a Lie algebra. And should I spell that out, or should I save time by leaving you confused? Yes? Remind you what Lie algebra is? No? No. Okay. It's a Lie algebra, and the second property, so it's R bilinear, skew symmetric, and there is a Jacobi identity. And the second one is that it's a derivation with respect to the, if you have two functions, you can multiply them. There is a algebra structure, commutative algebra structure, and what you want is something like this. Right? So I've defined, so I haven't told you, I just told you that I want to define one of these things. So up to sign, this Poisson bracket is defined as follows. Since the symplectic form is non-degenerate, we have an isomorphism. We have isomorphism of vector bundles. So if I take, so what does it do? It takes a point and a vector sticking out of it. So I'm thinking of V as the tangent vector at some point Q. And it sends it to omega at that point Q with a V plugged in. Right? And that's an iso of vector bundles. And hence, we have an isomorphism of modules of sections of these bundles. Let me just call it omega sharp again. So these are one forms. These sections are one forms. These sections are vector fields. So given a vector field, I can plug it in one point, and I get a one form. Right? So I haven't used all the block vectors yet. We define the Hamiltonian vector field of a function let me give it a name. Since all the symbols in symplectic geometry are overworked, I think I'll use Gilman's convention. I'll call it chi-sub-f. So that's the vector field by, let's see, chi-sub-f is omega sharp inverse of df. Or, if you like, if you plug in the Hamiltonian vector field in the first slot, you get df. Okay? And warning, some other people, meaning half the time the other sign is used. And in fact, the whole lecture should really be done with the signs modded out, because at some point I'll get into what's known as symplectic monodromy, where you pick certain conventions, you go around, and you discover that you're off by a sign. This is a joke, you're supposed to laugh. Well, maybe it's not a joke, because I will be off by a sign. Right, and so I haven't defined the, so we define, I want to, so definition f bracket g is the Hamiltonian vector field of f acting on g. Again, other sign convention is also used. So you start seeing that there are 2 to the n sign conventions, where n is large. Let's see. So let me check that if I define my, I'm sorry, I apologize. I'm being a little bit jet lagged. I got off the plane yesterday. Do you want me to check, is it clear why the second property is there? Right? Is it clear why, if I define Poisson bracket this way, why this will be? Yeah, that's just the definition of a vector field, right? Let's check the skew symmetry. It's clear that it's, well, let's see. It's clear that it's R bilinear, I think, from my definitions, right? If I multiply a function by a scalar, the vector field gets multiplied by a scalar. If I multiply g by a scalar, well, the scalar will come out. Skew symmetry. Let's check. I need to do this computation anyway. So f bracket g by the definition is Hamiltonian vector field of f applied to g. Let's see, what is it? This is the differential paired with the vector field, right? But what's the differential of g? That's omega with the c sub g stuck into the first slot, blank paired with c sub f. So I'll use these brackets for pairing between vector fields and one forms and between vectors and covectors, etc., etc. And I get omega of c sub g c sub f. Right? So the Poisson bracket you can think of as taking 2 vector fields, 2 Hamiltonian vector fields, and plugging them into the symplectic form. Right? And so out of this you see right away that this is minus because the symplectic form is Q-symmetric, and you get minus G bracket F. What else should I see? Okay, I will not prove the Jacobi identity. Just to save time, it follows from d omega equals 0. So if you write out the formula for d of omega and stick in 3 Hamiltonian vector fields, the Jacobi identity will pop out if you do it right and not screw up the signs. Wait. I don't want to write too low because I'm thinking that if I write at the bottom of the board, that nobody will be able to read it in the back. Is that correct? How low can you read? Is this about as low as I should go? Yeah, okay.
Theoretically for
Sorry?
here. How it's okay, you can write.
It's okay. Okay, so there's one more thing I want to prove. So let me put a claim up here. And it will be useful for us that if I take the bracket of 2 Hamiltonian vector fields, that's the Hamiltonian vector field of the Lie bracket, of the Poisson bracket. Hence, the map from smooth vector fields, smooth functions to vector fields is a map of Lie algebras. Okay? So you can think of this. Notice that this map is not injective because if I have a why is it not injective? What's in the kernel? Locally constant functions, right? I'm not assuming that my M is connected, right? So it's an extension. Okay, so let's prove it. You see, for the last month or so, I've been teaching undergraduates linear algebra, and they're really bad at it. So that's why I keep checking if people are following me. The linear algebra I'm teaching is to people who are going to go into math education, and for some reason they're not the fastest students we have, unlike in the engineers. Okay, so I'll stop complaining and start lecturing. So for any 2 vector fields, I can take I can contract a vector field with a 2 form, and I can take the Lie derivative, right? So let's see what happens if I do that. On one hand, it should be the bracket contracted with the 2 form plus the contraction of the Lie derivative. Right? Now, if I compute the Lie derivative of the symplectic form with respect to a Hamiltonian vector field, let's see what happens. By Cartan's formula, it's the contraction plus, right? I'm using Cartan's formula for the Lie derivative. Now let's see. D omega is 0 because omega is a symplectic form, right, by definition. And here I get, let's see, what was my definition of the Hamiltonian vector field? I get d of df, and I get 0. So it's worth noting that the flow of a Hamiltonian vector field preserves the symplectic form. Always. All right. Now let's see. Now if I can. Sorry. Okay, so let's see. If I look at the so let me take x to be the Hamiltonian vector field with respect to one function, and y a Hamiltonian vector field with respect to another. Then this equation still holds. This piece is not there, right? So maybe I should write 0 plus this. This is the Lie derivative of the Hamiltonian vector field of the contraction, right? Well, let's see. This is D. Looks right. And let's see what happens here. This is, I think we already computed this once, that this is 0, right? This is contraction of the Hamiltonian vector field with omega, that's dg. D of dg is 0. Contractive is something, doesn't matter, so this thing is 0. And what's left here? This is omega of Cg. It's d of omega of Cg Cf. Let's see, omega Cg Cf, this is d of the Poisson bracket, right? Using this. So the whole thing is d of the Poisson bracket. And by the definition of the Hamiltonian vector field, right? It says that this vector field is, so that tells me that the Hamiltonian vector field with respect to the bracket is the bracket of two Hamiltonian vector fields. If you flip signs in a few places, you might get a minus there. All right. So I have a symplectic manifold. Let me define periodic functions. So definition. I guess you were probably expecting my function to be defined on the real line or to be repeated when I shift things by integers, but I'm going to define f to be periodic of period 1 if the flow of, well, let's see, what should I call the flow? Phi of sub t of the Hamiltonian vector field of f is periodic with period 1. Right, this is more or less the standard definition of a periodic Hamiltonian. Right, so I want that phi f of t plus 1 is phi f at the time t. Right, and so periodic. So I should have said a Hamiltonian. Right? And you may have noticed that in symplectic geometry, people don't want to call functions functions, they call them Hamiltonians. For no good reason. They're just functions. So a periodic function f on m omega defines an action. Well, if I just have any function, then the flow of its vector field, I'm tacitly assuming that all of the flows are complete. They define the actions of the real line. If it's periodic, it defines an action of R mod z. Right, and what's the action? So if I have a equivalent class of the time t, so t up to prime 1, it acts on the point of a manifold by phi of t of x. So for all x in M, for all t in R mod z. And again, I should probably warn people that for me, a circle is R mod z. For some people, it's R mod 2 pi z. But 2 pi should have been set to 1 years ago. Now, suppose I have a whole bunch of these periodic functions. Then I have, well, it's not clear I actually get an action of a bunch of circles. I need to assume something else, right? I need to assume that the flows actually commute. Suppose we have n periodic functions, mu1 through mu(n), and their flows commute. Oh, one thing I'm terribly sorry for, I forgot to give you an example of a periodic function, right? So let's take m to be r cross r mod z. So let's call this variable p. Maybe I'll call this variable q. And I can take the symplectic form dp wedge dq. And I could take f of q p to be just p. Right? And let's see, what's the Hamiltonian vector field? So df is dp, which is the contraction of minus ddq with dp wedge dq. Right? And the flow of ddq is a periodic flow of period 1. And I guess secretly this is the cotangent bundle of R mod z. Okay, so suppose I have whose flows commute. Let me make a stronger assumption, right? So if I want the flows to commute, then I want the Lie brackets of their Hamiltonian vector fields to be 0. But remember, I actually have an extension of vector fields by smooth functions. So the assumption I'm going to make that their Poisson brackets are 0. Then the brackets of their Hamiltonian vector fields is 0. And that tells me that the flows And then this is for all I and j. So we get an action of the n-torus, which I am thinking of as R mod z to the n. You can also think of it as Rn mod z to the n on M given by so if I take a bunch of an equivalence class of vectors in here and apply it to a point in my manifold M, this is just a bunch of flows composed in some order. Right, and the order is not terribly important because they commute. Right, so such an action of Tn on M omega is called Hamiltonian. Well, it comes from a bunch of Hamiltonian vector fields. And, well, I can put mu into one function. This is called a moment map. All right. Right. I'm going to make an assumption that the action of my torus is effective, i.e., if some point fixes, if some time t fixes all x's, then this is the class of 0. Right? Let me emphasize for all x. I'm not assuming that there are no fixed points. There might be some points fixed by all time, but nothing fixes everything. We'll see. This implies that there exists open dense set, I don't know, I'm calling it M regular, where Tn action is free. This is because the torus is abelian. There are examples of group actions where the action is effective, but the action is not free in an open dense set, right? This is because the torus is abelian. If I look at the action of SO3 on S2, where I take the sphere and just rotate it, is effective, but free nowhere. So this is sort of an aside. Keep an example, right? Tori are different from other Lie groups. Does it make sense? No? Did I lie to you? The point is that the stabilizer at every point, or the stabilizer at different points are different. So nothing fixes everything, but there's always a stabilizer. It's just rotations around different angles, different axes. Right, and that tells you that for a generic point of M, meaning for a point in open dense set, the well, let me call it X of M, the map from the torus to M that takes an element and just pushes X around. Here's this is Tn, is an embedding. Right? If the action is free, your group is compact, then the orbit is embedded. We'll prove for Hamiltonian actions, Tn actions, orbits are always, all orbits are isotropic. And at this point, not writing this lecture on the plane, I should probably pause and think. If I assume you guys don't know what a Poisson bracket is, should I know that you know what isotropic means? Everybody knows what it. Should I quickly define isotropic? Yes. That just says that if I look at the tangent space to a point, to one of these orbits, and I look at the symplectic perpendicular, so let me give you a slightly different definition. This is a better one. For any pair of tangent vectors to the orbit, I'm putting the same point here, it doesn't matter. Omega VW is 0. But that, so linear algebra then tells you that the dimension of Tn dot x has to be less than or equal than 1/2 dimension of M. Right? The dimension of isotropic spaces could not be too big. Right? So that tells you that n has to be less than or equal than 1/2 of the dimension of M. Because generically the orbits are embedded. This is for all x. Right? So at some points, this is a copy of the torus. And all of a sudden you realize that if you have a Hamiltonian torus action, the dimension of the torus could not be very big. It has to be less than 1/2 the dimension. So here's a definition. A symplectic let me keep my group in the definition. Tn toric manifold is a triple M omega mu from M to Rn. So this is actually an n-tuple, right? It's a bunch of functions. So that the map mu1 through mun generates an effective Tn action, and here's the condition, n is half the dimension. Here's an example. Right, so a circle action on the cylinder with this symplectic form, well, 1 is 1/2 of 2, so everything works. And the action is free and Hamiltonian. Here's another example. Right, so after what? 45 minutes, I've defined what we're talking about. How many minutes do I have? 25?
Yeah, 25 or 30 minutes.
Here's another example. Let's take, so S1 acts on, so now I'm thinking of it as R mod 2 pi z. Let's see, what did I do? S2 round area form. So the symplectic form that I want to take is just, well, let's see. I can take the contraction of dx1 wedge dx2 wedge dx3 with the radial vector field and restrict it to S2. So here S2 is x in R3 norm x squared equals 1. Not an ellipsoid or anything of that sort. Nothing bumpy. So take that S2, take that 2 form by rotation about the z-axis or x3 axis. Right? So here's the picture. Here's the 2-sphere, and we're spinning it around. Then x up to scalar, a scalar, is a moment map. So up to, if I forget if I need to have a factor of 2 pi or minus 1 here. 2 pi is 1, minus 1 is also 1. Right, so up to a certain scalar that you have to stick in there, it'll generate this rotation. One way you can think about it, why this is, one way you can check the computation is write this area form in cylindrical coordinates. Right, this is vector calculus. Plug in the vector field that generates the rotations, and you'll see that the other coordinate in the cylindrical coordinates will pop out up to a sign. And then you have to check that the period is 2 pi as opposed to 1. Here's another example that actually is very useful for us. S1, now I'm thinking of it as unit complex number. Well, let's say S1, which R mod z, acts on C, and omega is square root of minus 1 dz wedge dz bar. I'll take this form. And the action is Here's the 2 pi's and i's multiplication. Right, so this form is really 2r dr wedge d theta. If I use polar coordinates, there is a 2 there, just to take care of things. And then mu of z, the moment map that generates all of this, is minus r squared, which is minus norm z squared. I was very sad when I discovered this minus sign.
But this minus sign is gone if you take the minus sign with quadratic.
Right, there are different ways of getting rid of this minus sign, including writing 1 over the square root of minus 1 there. But other people claim that that's the right choice of the signs. I'm not sure which convention you'll need. Right? And finally, a throwaway remark is if m1, omega 1, well, here things get a little hairy. Let's say mu1, m1, let's take mu I to r and I equals 1, 2, r2 symplectic toric manifolds. So 1 is, then I can take their product. So this circle plus means I take the forms on each of the factors, pull them up, and add them up. I'm suppressing the projection, pullbacks by the projection maps. Is also symplectic toric. So let me write an example here. But notice that I was abbreviating my example as EX, which also stands for exercise. Okay. So moment maps for Hamiltonian torus actions on symplectic manifolds on compact connected symplectic manifolds have a number of remarkable properties. So let me start with the first one, which is a theorem due to Sir Michael Atiyah. And to Gilman and Sternberg, independently. So let m omega mu m2 Rn. So I defined toric ones. Now I'm talking about just Hamiltonian torus actions, not necessarily toric. Toric means the torus is as big as possible. Here I'm not assuming that. Be a compact. Connected is just to You can always do it component by component. That's not a serious assumption. The compactness is important. Hamiltonian Tn manifold then two things. In the business, people refer to the first property as convexity. This is an X. Mu of M is a polytope, is a rational. In fact, it's a convex hull of the images of fixed points. It's not clear that the convex hull, well, first of all, it's not clear that there are fixed points, but there are. And that the images of fixed points is some collection of points, but it is. And it turns out that everything is just a convex. These are the vertices of the images of these things are the vertices and a few things inside the polytope. And the second one is that the fibers, so this is called connectedness. The fibers, mu inverse of C, C and Rn, are connected. Which is a little strange because if somebody hands you a vector valued map, vector space valued map, why on earth its fibers should be connected? Sorry? The set of fixed points is no, not all of them are actually. Some of them are symplectic submanifolds. Actually, they're not necessarily zero-dimensional.
But the image of them are.
The images are the images are isolated points. So let me talk a little bit about rationality. So recall a polytope. Maybe I should put recall in quotation marks, as in maybe you have never heard of this. But a polytope P in Rn is the intersection of finitely many half spaces. Right, there are two ways to think of polytopes: as a convex hull of finitely many points, or dually as intersection of finitely many half spaces. So I'm going to write P as I equals 1 to L X in Rn. Such that x dot vi less than or equal than ci for some v1 through vn vl in Rn, a bunch of vectors, and c1 through cl scalars. So a polytope P is rational if v1 through vl sit inside the integral lattice z to the n. It's so it being the polytope P let me call it unimodular. If for any vertex P of P, there exists exactly n. So this is, everything is sitting inside Rn hyperplanes. X dot V ij less than or equal than Cj. Well, maybe I'll put a different index here. Alpha equals I1 through In. This is not right. Alpha equals 1 through n.
It's a hyperplane.
Yeah, you can use either hyperplanes or the.
So it's equal.
Sorry. Thank you. I was going to ask if you were thinking of spanning the edges. Passing through P. And VI1 through VIN is a basis of Z to the n. Integral basis. Equivalently, there is a basis W1 through Wn of Zn, so that edges of P at lower P, lie on the rays P plus TWI. So this is I is between 1 and n. So let me give some examples. Right, and what I'm calling unimodular, Victor Gilman calls Dilzang, because Victor Gilman likes to name properties after people. I think unimodular has been around longer. So here are the examples. So I need a polytope, and I need a lattice. So here's my lattice, and so on. And here's the polytope. Here's P. Right, and if you look at the edges, or if you look at the normals, right, so here are the normals. And pairwise they form a basis, right? These two form a basis of Z squared, these two form a basis of D squared, these two form a basis of Z squared. Or if you look at the edges, right, these two vectors are a basis. So here's W1, W2, here's V1, here's V2. So this is unimodular. And it's easy to draw an example where it's not, it's much easier to draw an example where it's not unimodular. Something like this will do. So here's the lattice. Right? And you could see that these two vectors, this is not a basis of Z squared. So right there, things go wrong. I took too much space. So here's the theorem. So this theorem is, I guess, around 82, something like that. And here's a theorem due to Dawson. And that's late 80s. So if you have toric manifolds, then the polytopes become even more distinct, more specialized. Right? So let m omega mu be a compact, connected, symplectic, toric manifold. You won't be able to see it. Then, first of all, mu of m is unimodular, also called Dawson, but not by Dawson. And 2, that's pretty much all there is. For any unimodular polytope P in Rn, there exists, let's do it to I. There exists a compact, connected, symplectic, toric manifold. Let's call it MP, omega P, mu P, M2Rn, with mu P of MP being the polytope you started with. And then you have uniqueness. If I have 2 of them, are 2 symplectic, toric. So here is I is 1, 2. Are 2 symplectic toric Tn manifolds with the same moment map images. Then there exists Tn equivariant symplectic diffeomorphism, diffeo phi from M1 to M2, so that, well, I think I ran out of space, so I'll put it here. This diagram commutes. So this was state of the art as of early 90s, I guess. have, what, 10 minutes? 5 minutes. Oh, okay. So I was talking slow. Right, so let me, instead of writing on the board, let me tell you what goes into the proofs of these theorems. It's really Morse theory, right? So it turns out that various components of the moment map are Morse bot functions with all the indices even. Once you have a function whose indices are even, it should not come as a surprise that its level sets are connected. For Morse functions, it's certainly true. For Morse bot, you'll have to work a little bit because it depends on what the minimum is, right? Now I want to say a few words. Now suppose m omega mu m Rn is non-compact symplectic Tn toric manifold. Is there an analog of Delzon's theorem? Well, let me just say that things really look hopeless. First of all, no Morse theory. Well, no conventional Morse theory. Maybe you could play around with Conway indices, but I haven't seen anybody try. And two, fibers of moment map are not connected. And even when they are connected, image of the moment map tells you very little. So an example, so here's my example of 3. I can take m to be c minus the origin, take omega to be the one I've taken before. Mu of z is minus norm z squared. And I can take m tilde to be a map from c minus 0 to itself, which is n-fold cover. If you like, z goes to z to the n. Right. Now if I pull everything back, m tilde, omega tilde, which is pi pullback of omega, mu tilde, mu composed with pi, is again power mod z symplectic toric manifold. Right? And the moment map image is exactly the same. So the moment map right, so you don't have anything like that. And I guess I need another 5 minutes to tell you what the answer is. Maybe I should stop here?
It's up to you.
I can talk for another half hour. I think it's better if I stop here.
Okay, any questions?